Hello everyone. The title of this video is Graph Logarithmic Functions. In this video I'm going to be doing exercises that are taken directly from a free online textbook at openstacks.org, and it's their Intermediate Algebra 2nd edition text. I'm in section 10.3 titled Evaluate and Graph Logarithmic Functions, and I'll be working under the heading Graph Logarithmic Functions. Now I'm only going to be doing the even numbered exercises, the ones that don't have a link to solutions, or the odd numbered ones have a link to the solution, so I won't be doing those. So that'll be exercise 178, 180, 182, 184, and 186. Right. I will also have timestamps for these exercises in the description of the video below. So if you look at the description, you'll see example 1's timestamp will be for the start of 178, example 2 for number 180, example 3 for 182, and so on. I also request of you that when I start a new question, pause the video and try to work on it yourself first before watching me doing it and compare. Because if you're just watching me do the questions and not practicing yourself, chances are you're not learning all that much. Alright, so in each of these exercises we are simply asked to graph each logarithmic function. Alright, so in each of these we have y equals an expression, a logarithmic expression dependent on x, right? Or they would say that y is a logarithmic function of x. And number 178 is example 1. I have that written out. So example 1, exercise 178 from the text. And we're asked to graph each logarithmic function. Alright, so we have first one, we have y equals the logarithm, base 2 of x. Right. Now, don't forget that a logarithmic statement is equivalent to an exponential statement. Y equals the log base 2 of x is the same thing as saying 2 to the y power equals x, or x equals 2 to the y. And we could plug in values of y and get values of x and then plot ordered pairs. But noting this though gives me an idea as to what I should be plugging in for x. Right, according to this statement, x should be some power of 2. Right, so that's what I'm going to do. I'm not going to write this out for the next examples, but I'm saying y equals the log base 2 of x. So what should be inside the parentheses here? What should I input is powers of 2. Right, I want to put powers of 2 into this to make it easy on myself. Right. But it all depends on the base of the logarithm. Okay, so when and just like any other function, I'm going to make a table. This is an xy table, and we'll see what ordered pairs we're going to plot on the xy plane. And as I said, I'm going to put in powers of 2. So, 2 to the 0, 2 to the negative 1, 2 to the negative 2, 2 to the first, 2 to the second, and so on, right? Now 2 to the 0, that's going to be 1 for x, right? And remember, 2 to the first is 2, 2 squared is 4, 2 to the negative 1 is 1 over 2. Remember, the negative powers are just the reciprocals of the positive powers. 2 to the negative 2 is 1 over 4, right? 1/4. So these are going to be my inputs, right? The inputs will be powers of 2. powers of whatever the base on the logarithm is. And then the output is just the exponent on those powers of 2, right? So we have x equals 2 to the y, so y is just the exponent on those powers of 2 that I'm plugging in. Right, so remember the log base 2 of 1, right, if I plug in 1 for x, that's 0, which again is just the exponent on that power of 2 I plugged in for x. And the log base 2 of this x value, the log base 2 of 2, is just 1. Again, remember, logarithms are just exponents. This is just the exponent on that power of 2 that was plugged in. Then the log base 2 of 4 is 2, right? 2 to the second power is 4. The log base 2 of 1/2 is -1, right? Since 2 to the -1 power is a half. And the log base 2 of 1/4, right, when I plug in 1/4 for x, is -2, since 2 to the -2 is 1/4. And I can keep doing this. Right. So I got a bunch of ordered pairs here. 1/4 -2, that's a point. 1/2 -1 is a point. 1, 0 is a point. 2, 1, 4, 2, and so on. Alright. So I'm going to make my xy plane. X-axis horizontal, y-axis vertical. And looking at the x values that are used here, we have an x value of 1, an x value of 2, an x value of 4, an x value of 1/2, an x value of 1/4, and then the outputs are just integers: 0, -1, -2, +1, +2. So I mark those off, and let me plot some points. So we have 1/4 input, -2 output. There. 1/2 input, -1 output. 1 input, 0 output. 2, 1, 2, 1. 4, 2. 4 input, 2 output. Alright, and maybe you see this. These points are kind of following along a graph that is going to look very similar to an exponential function. Right? I'm hoping you remember how your exponential functions look. Only instead of y equals 2 to the x, it's x equals 2 to the y. Right. So if I start from 1, 0 here, as you move to the right, the graph would go up higher and higher, just very, very slowly. Right? I'd have to go out to 8 to get 3 as an output. Right? I'd have to plug in 8, which is 2 to the third power, to get an output of 3. Right? That would be the log base 2 of 8. Right? So you'd go out to 8 to get an output of 3. You'd go out to 16 to get an output of 4. Right? But it would eventually get higher and higher. All right, and then if I move left of the point 1, 0, see, I curl down to this point here, getting closer to the y-axis. Then to this point here, getting closer to the y-axis. Like the exponential functions had a horizontal asymptote, these logarithmic functions have the y-axis as a vertical asymptote, right? So I'll make this a little highlight the y-axis here. X equals 0, the y-axis is a vertical asymptote for this logarithmic function. All right, the graph will get closer and closer and closer to this y-axis without actually touching it. Right? And the reason for this is because of what I'm inputting, what I have to input for these logarithmic functions. Right? I told you a second ago, right? This is log base 2. So I'm going to be inputting powers of 2, right? 2 to the 0, 2 to the 1, 2 to whatever power, 2 to the y. Remember your exponential functions? Remember the range of exponential functions was all positive numbers. Powers of 2 are always positive. Right? And that's going to be the domain for any basic logarithmic function. You're only allowed to plug in positive numbers. So the graph of a basic logarithmic function will be all to the right of the y-axis. Okay, and then I'll put this on the Desmos site, but let me write out some properties here, right? So for this particular function we're looking at, again, the vertical asymptote, x equals 0, the y-axis, right? The graph is approaching that from the right side, never actually touching it though. Right, because if I plugged in 1/8, I'd get -3. Right, so get closer. Here's 1/8. You'd go down to -3 as the output. If I plugged in 1/16, right, get even closer to the y-axis, the output would be -4. So you see, as the input gets closer to the y-axis, as the input gets smaller and smaller, closer to 0, the output gets bigger negative. Right, it'll go down forever. Alright, so something else to point out is that this would be considered an increasing function. Alright, this would be considered an increasing function because as the input increases, the output increases always. Alright, so this is considered an increasing function. Pardon me. The domain is only positive numbers. Again, I was just plugging in powers of 2 here. You can only plug in positive numbers. So on the x-axis, the only numbers I can use are from 0 to infinity, but not including 0. Right? In parentheses on infinity always. And then the range, I guess I should have left more space here. The range is all real numbers. Look at this. It goes, the graph is going up forever this way. So every y value that's positive will be hit. And the graph is going down forever as it gets closer to the y-axis. So every negative y value will be hit as well. And 0 is hit at x equals 1. So the range is all real numbers. So this is important to remember up here as well. But yeah, and before I get to the Desmos site, before I go to the free online graphing calculator at desmos.com, I want to talk about this domain being only positives. That's a big note. You can only take logarithms of positive numbers. Right, because for example, what if I said what's the log base 2? What if I plugged in 0 for x? Well, say I don't know what this is, right? The log base 2 of 0 equals some question mark, right? I don't know what that is. Well, if I change this to exponential form, that would imply that 2 to some power equals 0. But this can't happen. Right? I said already, powers of 2 are going to be positive numbers. So this is undefined. right? The log base 2 of 0. And in fact, let me pull up a calculator here. I got a TI-84 simulator. I'll put in the log base 2, the log base 2 of 0, and you're going to see an error come up. Right? Domain. Right? You can only take a logarithm of a positive number. Right? Same thing for negatives. Now, I'm going to change this back to real mode. You see, right now I'm in A plus BI mode. If you look at the top of my calculation screen, I'm in complex mode, A plus BI, where remember I is the square root of -1 imaginary. Sure, when I plug in 0 to a logarithm, I get an error. But if you do log of a negative number, so say I wanted the log base 2 of -1, and I don't know what this is, right? It's equal to some question mark. Well, changing this to exponential form means, 2 to some power equals -1. Again, this can't happen in the real numbers, okay? This can't happen with real numbers. Alright, unfortunately it can happen with imaginary numbers. Alright, so if I punched in, if I kept it in A plus BI mode and said, what's the log base 2? What's the log base 2 of -1? You see it gives me an imaginary result. But if I go back to real mode, right, we should be in real mode here now because I'm graphing, right? When you're graphing on the XY plane, remember the x-axis is a real number line. The y-axis is a real number line. So I want real outputs only. So I'll just say, the log of a negative number is not real. It's imaginary. Right, but I'm not going to know how it's imaginary. Right? Just know that the log of a negative number is not real. Right? So now I go back and let's enter the same thing, log base 2 of -1, and it'll come back at me not real. Right? Okay, so just be careful with logarithms. Make sure that the number inside the logarithm is positive. Right. Okay. So yeah, so big note here. Definitely remember this when we're talking about, graphing, right, or inputs are real. I want the outputs to be real as well for these logarithmic functions. So the numbers I plug in can only be positive numbers. All right. Great. And now also let me show you this graph on that free online graphing calculator at desmos.com. So here it is here. And this is a free online graph calculator, desmos.com. And I'm going to put in, y equals the log, make sure you got a subscript of 2, the log base 2 of x. And you see this graph, looks pretty much like the graph I had. And you see how it's, the graph, as you go down here, the graph is getting closer and closer to the y-axis, but not actually touching it. See, this graph here is not actually going to be on the y-axis ever. And we could make a table. I have a table show up here and all these points plotted. See, -2, undefined. -1, undefined. 0, undefined. I have to plug in positive numbers only to this, right? So 1/4, 1/2. I'm plugging in powers of 2. 1, 2, 4, 8. Right? And you see these points that I plotted on my graph, right? There's a quarter, -2, a half, -1, 1, 0, 2, 1, 4, 2, 3, 8. 8, 3, sorry. You know, 1/8 -3. Say there's 1/8 -3, and 1/16 -4, and so on, right? Just seeing all these points here. 1/16 -4. But again, the y-axis, x equals 0, is the vertical asymptote for these basic logarithmic functions. It's an increasing function. The domain is only positive numbers, and the range is all real numbers. Okay. Great. All right, so let's go back now to our next example. So again, we have another basic logarithmic function. Y equals just a log with a base of x. Right. Y equals log base 6 of x. Right. So because this is base 6, right, I'm going to make sure that, just to make it easy on myself to plot points, you could plug in any positive number you want. Right? You can plug in any positive number you wish, but as long as it's positive. But to make it easy on myself, I'm going to plug in powers of 6. Right? Powers of 6. So 6 to the 0, 6 to the 1, 6 to the 2, 6 to the -1, 6 to the -2, whatever. All right, so go into my table here. Now again, 6 to the 0 is 1. Then 6 to the first is 6. 6 squared is 36, right? 6 to the -1 is 1/6. 6 to the -2 is 1/36. So on. So here I'm plugging in powers of 6. Notice that again they're all positive. Right? You can't plug in 0 to a log. You can't take the log of 0. You can't take the log of negative numbers, right? Those are not real. And the log base 6 of 1 is 0, right? This was 6 to the 0 power. This was 6 to the first power. The log base 6 of 6 is 1. The log base 6 of 36 is 2, right? That's 6 to the second power. And 1/6, that's 6 to the -1. Remember, y is just the exponent. Logs are equal to exponents. Y is just the exponent on that power of 6 that I plugged in. And the log base 6 of 1/36 would be -2. And I'll make a rough sketch of the graph by hand. Here's the xy plane. So I'm plugging in 1, 6, and you can go out to 36 if you wish. And then here's 1/6, and 1/36 would be even smaller, and 1/6 cubed, and 1/6 to the fourth, but always positive. All right, so I got these points to plot. 1, 0, input 1, output 0. Input 6, output 1. Input 1/6, output -1. And again, the graph will do like the graph of number 1 did when I had log base 2. It's going to be increasing as I move to the right, just very, very slowly. Right? It won't get up to an output of 2 until I get out to 36. It won't get to an input output of 3 until I have an input of 6 cubed, which is 216. All right, so it's going to be increasing, but just very, very slowly as I move to the right. And then as I move left, it's going to be shooting down forever, but all to the right of the y-axis, right? Again, the y-axis is a vertical asymptote. And I'll state that again, right? Dot in the y-axis here. Right? The graph will get closer and closer to the y-axis as x approaches 0. Y will approach, -infinity, but the graph will never actually touch So again, I have a vertical asymptote, which from here on out, I'll just abbreviate VA, right, for vertical asymptote. I have a vertical asymptote at x equals 0, right, the y-axis, yet again. Right, and again, we have an increasing function, right? As I move left, as the input increases, the output also increases, right? So we have an increasing function. Once again, the domain is positive numbers only. I can only plug in positive numbers for x, so from 0 to infinity, right, but not including 0. And the range, right, the y value is being used is everything, right? It's going to negative infinity here, it's going to positive infinity over there. Yeah, the every output is possible, every real number output. Right, so here's your, again, you should know this stuff about some basic logarithmic functions. Okay, great. And again, let me show you on the Desmos site this same function. So we're given y equals the log base 6 of x, right? And see that graph. And again, I can put a little table up in it. And once again, notice for -2 undefined, -1 undefined, right? 0 undefined. Has to be positive, right? 1/36, -2. 1/6, -1. 1, 0, 6, 1, 36, 2, 216, 3. 1 over 216, -3, right? And again, you're seeing these points plotted, and once again, if you zoom in closer and closer, you'll notice that the graph doesn't actually touch the y-axis. Right? You can zoom in far enough to where eventually you do see that the graph is separate from the y-axis, right? It never will actually touch it. X equals 0, the y-axis is a vertical asymptote. Increasing, domain is all positive numbers, right? The domain is only positive numbers, and the range is all real numbers, right? Going up and down forever and up forever. Just very, very slowly, right? Like I said, you have to go out to 36 to get an output of 2, right? And you have to go out to 216 to have it increase to an output of 3. Right? Well, I don't feel like scrolling that far. I guess it won't take that long, but you have to go out to 216 to get an output of 3. Here it is. And then you have to go out to 6 to the 4th power to get an output of 4. Right? It would take quite a long time, but it increases still, just very, very slowly. Okay, wonderful. Now our next question is going to be similar to numbers 1 and 2. We'll have y equals some basic log base something of x, right? Just x. And the base will again be something bigger than 1. And then after the third example, I'll just write out in general what a basic logarithmic function looks like when the base is bigger than 1, right? So far we've had a base of 2 and a base of 6. And in example 3, I have a base of 1.5. Right? So y equals log base 1.5 of x. Right, so once again, I want to put in powers of 1.5, right? Some nice integer powers of 1.5. Now 1.5, right, that's also 3 halves, so you could also think of this as the log base 3 halves of x. Same thing. Okay, so I'm going to make a little table. And then, anything to the 0 power is 1, so I'm going to plug in 1. And again, I have to plug in positive numbers for x here. The number inside the log has to be positive. Now, 1.5 to the first power is, 3 halves to the first, that's 1.5, right? 1.5 squared to the second power, that's 9/4, or 2.25, and so on. And then I can go backwards, go negative powers of 1.5, right? Now, 1.5 to the negative 1, that's 3 halves to the negative 1, that's just 2/3, right? The reciprocal 2/3, or 0.6 repeating. And then to the negative 2 would be 4/9, 0.4 repeating. Right? So I plug in these values for x, these powers of 1.5, and I'll get, negative 2 here, negative 1 here, 0 here, 1 here, 2 here, right? Just the exponents on 1.5 from these powers of 1.5 that I plugged in. And then once again, a rough hand drawing of the xy plane. I'm plugging in, here's 1, here's 1.5, 2, and then, let's say 3, and then 2.25, right, 2.25 there. Then 2/3, say about here, and 4/9 is a little under a half. Let's say that's here, right? And I get my outputs of 1 and 2 and -1, -2. And let's plot these points that we have in our chart. 1, 0 again. That's going to be on all these basic logarithmic functions. 1.5 input, 1 output. 2 and 2.25 input, 2 output. All right, so this one looks like it's increasing a little more rapidly, but still slowly compared to an exponential function. 2/3, -1. 4/9, -2. Right, and again, we have something that looks like an exponential function, but this way. Right? It's all to the right of the y-axis. So it'd be going up forever that way and down forever, but to the right of the y-axis. Once again, the y-axis is a vertical asymptote, right? VA x equals 0, the y-axis. The graph will get closer to it, but never actually touch it. All right, and then once again, the function is increasing. See, as you move to the right, the graph is going up, right? The outputs are increasing. The domain is only positive numbers, right? You can only plug in positive numbers to a logarithm and get a real number output. So from 0 to infinity again, but not including 0. The range is once again all real numbers, right? It's going down forever, up forever. So all real numbers, negative infinity to infinity. And let's take a look at this on Desmos, just to verify that my drawing is decent. Y equals, right, the log with a base of 1.5 of x, right, and there it is, just like my drawing. I'll add a little table to this. So again, notice -2 input undefined, -1 undefined, 0 undefined. Got to be positive inputs. So 4/9, right? -2, 2/3, -1, 1, 0, 3 halves, 1, 9/4, 2, right, and so on. Okay. All right, here's all the points I plotted by hand. But again, you can do more, right? If you were to plug in 27/8, you'd get 3, right? 27/8, 3. And then 81/16, oops. Then 81/16 would give you 4, right? And the reciprocals of those, right, would give you the negative powers, right? 8/27ths for -3, an input of 16/81ths. Right, 16/81ths would give me an output of -4. Right? And the closer to 0 x gets, the bigger negative the output is. Right? And the bigger x gets, the bigger the output, right? It's an increasing function. Domain is positive numbers, range is all real numbers. Great. All right, next question. Well, actually, before I get to the next question, we've seen 3 logarithmic functions now, 3 basic, it's just a log base something of x, right? There's no x plus 3 or 2 times x or anything added to it, multiply, it's a very the basic logarithmic function. And every one we've seen so far has had a base bigger than 1. Right? And don't forget, we've seen logarithms before. We're only dealing with positive bases, no negative base logs. That gets a little weird, a little hairy. But in general, okay, what we've been seeing is the following. So in general, given y equals the log base b of x, if the base is bigger than 1, as we've been seeing in these examples, base 2, base 6, base 1.5, then the graph will look like this. And it'll look very similar to what we've been seeing. Say here's 1 for x, and then b is bigger than 1, so let's say b is out here, and then 1 over b would be less than 1. Right? There's an input of 1 over b, and output 1 when you plug in b, output -1 when you plug in 1 over b. You'd have these points, right? You'd have the point 1, 0, b 1, and 1 over b -1. And you could go b squared 2, b cubed 3, 1 over b squared -2, 1 over b cubed -3. But the graph will be one of these, increasing logarithmic functions, right? Just increasing very slowly, and has the y-axis as a vertical asymptote. Right? X equals 0 is a vertical asymptote. The graph will never actually touch the y-axis, and it'll be an increasing function. The domain is just positive numbers, and the range is all real numbers. And that's not going to change for any of the basic logarithmic functions. The domain will be all positive numbers, and the range will be all real numbers. What's going to change with the different bases is whether or not it's increasing, right? Increasing or decreasing. But when the base is bigger than 1 on these basic functions, the function will be increasing, and it's all to the right of x equals 0. For the domain is positive numbers only. Okay. All right, now we're going to look at some examples where the base is less than 1, but still positive, right? Still positive bases. Right, so example 4, I just got a couple of these. Right, so here's y equals the log base 1/3 of x. Right, so now the base is still positive, but less than 1. Let's see what happens. Alright, so I'm going to put in powers of 1/3 for x, right? Positive numbers only. 1/3 to the first is 1/3. 1/3 to the 0 is 1. 1/3 squared is 1/9. And 1/3 to the -1 would be 3. 1/3 to the -2 would be 9, right? So you get -2 for that input, -1 for that one, 0 for that one, 1 and 2, right? The exponents on the power of 1/3 for all these. And let's plot this by hand, and then I'll go to the Desmos site as well. Alright, so my inputs are, 1, 3, 9, then 1/3 and 1/9, right? Really tiny stuff, tiny inputs. And my outputs are from -2 to 2 on the y-axis. Alright, let's plot these points. So again, you got 1, 0, right? Input 1, output 0. Input 3, output -1. So see what happens here? It's going to be a decreasing function. As x increases, the output will decrease, will go down, right? Input 9, output -2. Input 1/3, output 1. There's 1/3, 1. Input 1/9, right? An even smaller input. You get a bigger output, 2. Right? And if I plugged in 1/27th, right, an even smaller input, the output would be 3. So the closer to 0 we get for the input, the larger the output. And the bigger the input, the smaller the output, right? It goes down forever. But you're going to see it decreasing, very slowly, right? Again, decreasing, but very slowly. I'd have to plug in 27 to get an output of -3. I'd have to plug in 81 to get an output of -4. But still, it's going down forever that way. And then, again, only positive inputs. Only positive inputs. But as the input gets smaller, the output gets larger. Going to infinity on the right side of the y-axis. But still, the y-axis, right, x equals 0, is a vertical asymptote. The graph will never touch the y-axis. But it gets really, really close to it, as close as you want, without actually touching. Now this time, though, as I said already out loud, this is a decreasing function. As the input increases, the output decreases. All right, so that's going to be the only major difference, right? The domain and range are the same as before. Right? The domain is still only positive numbers. Right? I can only plug in positive numbers into. I can only take logarithms of positives in order to get real number outputs, and the range is all real numbers. Right? The only thing that changed, when the base went to being, instead of above 1, the base is less than 1, it went from an increasing to a decreasing function. That's really the only thing that changed here. All right, and once again, I'll pop this up on the Desmos site. So right, we had y equals the log base 1/3, the log base 1. Oh man, I can't enter this for some reason. All right, let me do this instead. Look for functions in the keyboard. Miscellaneous. And they do have a log base a here, and then I can put in, hopefully, nope. Why can't I enter this? Log base. This is something else, isn't it? Oh, maybe if I do this. Maybe if I do this. Sorry about this. Now put a fraction here. See if they have like a little fraction thing. No. Okay, this is a bit annoying. We can't really enter this fraction base. That's unfortunate. Well, so instead of in Desmos, let me pull up my TI-84 calculator, and we'll do it there. Alright, so we got, let me get rid of the, alright, so let me go and graph, y equals, so sorry about this, looks like fraction bases are tough to enter in Desmos for some reason, but we have log base 1/3, unless I'm just not doing it right. Log base 1/3 of x and graph, and you see now it's not as nice as Desmos, but you see it is a decreasing function. If I go to a table, you see how it has an error at 0. In fact, I'm going to have table setup and just change it to independent to ask, so I can plug in whatever I want for x and then go back to the table. And yeah, you see if I plug in 1, output 0. Right? 1/3 outputs 1. 1/9 outputs 2. 1/27 outputs 3. Right? The smaller the input gets, the larger the output gets. And then plug in 3, you get -1. Plug in 9, you get -2. Plug in 27, you get -3. Right? The higher the input gets, the smaller, the more negative the output gets. And I know you can't see it because it looks like it stops, but the graph actually shoots up. That's like the limitations of some of these TI calculators. That's why I like Desmos more. Now there is a way to graph on Desmos with a fraction base. It's just for some reason I couldn't enter the fraction where it was. So let me actually go back to Desmos. I'm sorry. And show you that you can enter it with, we haven't talked about this yet, but it will come up in a future video, something called the change of base rule. I can go log of x and then divide it by the log of 1/3, and this is the log base 1/3 of x. Alright, and let me show you with a table. If I make a table, see this decreasing red function here? If I put a table in this, see, for negative values and for 0 it's undefined, sure, but if I plug in, right, it was, let's go 9, right, see, -2. Plug in 3, you get -1. Plug in 1, you get 0. Plug in 1/3, you get 1. Plug in 1/9, you get 2. So this is the log base 1/3 of x, just written in a weird way. Like I said, we'll talk about this change of base rule. How do I rewrite logs like this? We'll talk about that in a future video. So yes, I can't seem to enter a fractional base on a log, but I can do it this way. Alright, but yeah, vertical asymptote at the x-axis again, right? You can zoom in as much as you wish and see that the red graph doesn't actually touch it. The domain is positive numbers only, the range is all real numbers, and it's a decreasing function, just like in my drawing. Alright, wonderful. Alright, so now the last example before I just write out in general what a basic logarithmic function with a base less than 1 looks like. Alright, so here we have y equals the log base, 0.4 of x. Again, this base is less than 1, but still positive, right? We're always dealing with positive bases. And you could also think of this, if you don't like 0.4, right? That's 2/5, right? The log base 2/5 of x, same thing. All right, so once again, I'm going to make a little table over here where my inputs are going to be powers, nice integer powers of 0.4 or 2/5. So 2/5 to the 0, that's 1. So I've got 1, 0. Remember, y is just the exponent on 2/5, right? The logarithm base 2/5 of what I'm putting in. 2/5 to the first is 2/5, or 0.4. So you have 2/5 1. Then you have 2/5 squared is 4/25, or 0.16. So 4/25, or 0.162, and so on. So the smaller the input gets, the larger the output gets. And then, plug in the reciprocal of 2/5, right? 5/2, that's 2.5. Get an output of -1, right? 2/5 to the -1 would be 5/2. So 5/2 input, -1 output. And then square that, 25/4, or 6.25 input, -2 output, and so on. So the larger the input gets, the smaller the output gets. So you're going to see that this is a decreasing function again when the base on the logarithm is less than 1. Alright, so input 1, and then you got here's 2, 3, and then 5/2 would be here, right? 2.5, 2.5, then 4, 5, 6, 7, there's 6, there's 7. 25/4 is 6 1/4, so there's 25/4, and then 2/5 is 0.4. Let's say that's 2/5 there, and then 4/25 is 0.16, so even smaller, right? 4/25, and the outputs are -1, -2, 0, 1, and 2. And we plot these points. So you got 1, 0 again. Right. This is fading away. Let me throw that out. So 1, 0. Got 5/2, -1. 25/4, -2, right? 6.25, -2. 2/5, 1, right? 4/25, 2. And if you did, 8 over 125, right? Really, really small. 0.064 or something, be 3, right? So again, it's doing that decreasing thing, right? Where as you move to the right, as x increases, the y value decreases. And as x gets really tiny, the y value would get really large, right? Again, you have the the y-axis, right? X equals 0 is a vertical asymptote. Once again, right, sorry, that's crappy. But the graph will get closer and closer to the y-axis as you go up, but never actually touch it. And once again, this is a decreasing function. And the domain and range are the same as it's been through all these basic log functions. Right, the domain is all the positive numbers, or you can only plug in positive numbers to a logarithm. And the range is all real numbers. Right? The range is all real numbers, goes up forever and down forever and everything in between. Right? And then once again, I'm going to enter this on Desmos. Now this is a decimal. If I tried to enter the fraction, it would be bad. You saw that with the last example. I apologize about that again. But this is a nice decimal I can enter. Right? This should work out on Desmos pretty easily. So y equals the log with a subscript, right, with a base of 0.4, right, that actually stays there, of x, right, and here you go, and there's that decreasing function. Let me make a table again. So again, notice negative inputs, 0 input, undefined, right, not real. Let me just put in the stuff I had, 25/4, which is 6.25, right, that gave me -2. 5/2 gave me -1 as an output. 1 gave me 0. 2/5, right, 0.4 gave me 1. 4/25, or 0.16 gave me 2, right? And these are the points that I plotted on my hand drawing. And again, you can zoom in and see that the graph doesn't actually touch the y-axis. The domain's positive numbers, it's a decreasing function. Range is all real numbers. All the same stuff as you saw in example 4 as well. Great. All right, so let's go back. And that's it for the examples I'm going to do. But notice, hopefully you noticed in example 4 and 5, had a very basic exponential function with a base that was less than 1. And they were decreasing functions, right? So in general, so again, we're given y equals the log base b of x, right? A very basic logarithmic function. This time, if the base is between 0 and 1, right? It's still positive, that's why I have it greater than 0, but if it's less than 1, like 1/3 or 0.4, as we saw, then the graph will look like this. So again, input 1 will give me an output of 0, but this time b is less than 1, so b, let's say, is in here. There's b less than 1. And then 1 over b would be greater than 1. So let's say 1 over b is over here. An input of b would give me an output of 1, right? B to the first is b, and b to the negative first is 1 over b. So an input of 1 over b would give me an output of -1. And then I have these points, right? 1, 0 is on all these basic logarithmic functions. b, 1, 1 over b, -1. And you can see it's one of those, again, decreasing functions with the y-axis is decreasing very slowly. Right, but the y-axis is a vertical asymptote. Right, x equals 0, the y-axis, vertical asymptote. Right, the graph will get shoot up forever, get closer and closer to the y-axis, but never actually touch it. It's a decreasing function. The domain is all positives. Right, only positive numbers can be. You can take the log of only positive numbers. And range, right, goes up forever, down forever, no gaps, right? The range is all real numbers. Right? Great. All right, so I'm hoping that after all these examples that what you take away is the basic shapes, right? When the base is bigger than 1 for y equals, the basic log base b of just x, increasing function, all to the right of the y-axis. And when the base is less than 1, right, but still positive, for these basic log functions, y equals the log base b of just x, it's a decreasing function. Right? Domain for both, domain is positive numbers, range is all real numbers. Right? Okay. I'm hoping that that's what you take away from these examples. And that's it. So I'm hoping that watching me go through these 5 examples here help you in some way, when you're asked to graph some basic logarithmic function, right? Again, a very basic one, just a log with some positive base of x only. When you're asked to graph that stuff on your own, I hope this helps. Right, and thank you very much for watching.